So we'll move to the theory part next. Move to the next of the theory part, analysis of bivariate data. Data collected on two variables together is called as bivariate data. Again, we can have discrete data as well as continuous data. This is the raw data or the discrete, where the pair of observations x and y, for example, age and height of the student, marks in subject 1 and marks in subject 2, height and weight of the students are collected. If we have many repetitions in x and y, you could prepare a frequency table. So if you refer practical 1, construction of frequency tables, you have generated bivariate tables for the given pair of x and y, and that is called as frequency or continuous data, where you could have discrete values here or you could have class interval data. So frequency data, raw data. So we will have discrete frequency, continuous frequency, as well as the raw data x and y here. Now the analysis, where here we mainly deal with two cases here, correlation analysis as well as regression analysis. Coming to the correlation, the word correlation is nothing but mutual relation, correlation, relation between two variables here. Here, out of all possible relationship, we only talk about particular case which is linear relationship, that is a straight line relationship between a and x and y. So if you have y is equal to a plus b into x, then we say x and y are linearly related. In this case, x is said to be the independent variable and y is said to be dependent variable. Now in case of the correlation analysis, we are not interested in the actual relationship, but we are only interested in telling whether linear relationship exists or not. If so, what is the degree of the relationship? That's what we discuss here. Now coming to the types of the correlation, based on the types of sign of the value of the correlation, you could categorize correlation into positive correlation, negative correlation, and the third case is no or zero correlation. When you observe that an increase in y leads to the increase in x leads to the increase in y, then we say x and y are positively related. For example, say as age increases, the height of the child increases. So x age is increasing, y the height of the child is also increasing. So both x and y move in the same direction. On the other hand, you could say that a decrease in x will lead to a decrease in y. For example, marks in subject 1 is being decreasing. Along with that, we observe that the marks in subject 2 is also decreasing. So together I can say that if x and y move in the same direction, then we say correlation is positive. If they move in the opposite direction, that is an increase in x will lead to decrease in y, or a decrease in x will lead to increase in y, in that case we say correlation is negative. If the change in one variable is not at all associated with a change in the other variable, then we say there is no correlation between x and y, or we say the correlation is zero. Now sometimes we might have a case where x and y are not linearly related, but they are related in any other form, like a parabolic relationship, quadratic relationship, or a logarithmic relationship, exponential relationship, and so on. In that case also we say x and y are not linearly correlated. Not linearly correlated is also said to be zero correlation or no correlation. Again, based on the number of variables also we could categorize the correlation here. So correlation based on the number of variables. If you are talking about only correlation between two variables x and y, then the correlation is said to be simple correlation. If you are talking about more than two variables, then we say correlation be multiple correlation. Say you have three variables x, y, z, four variables w, x, y, z, then comes the concept of multiple correlation. Out of the many variables, if you pick only two, so you have three variables but you are concentrating only two, ignoring the effect of x, then we say the correlation is partial correlation. So we'll stick to the simple correlation between x and y. So I have understood the concept, right? Correlation, the degree of linear relationship, the linear association between x and y is said to be correlation. Linear, in simple words you can say amount of linear relationship. Amount of linear relationship between two variables is said to be correlation. Correlation is amount of linear relationship between two variables, say x and y. So that is how correlation is defined. So types of correlation: positive correlation, negative correlation, no or zero correlation. What is positive correlation? Increase in x leads to increase in y, or decrease in x leads to decrease in y. Negative correlation: an increase in x will lead to decrease in y, or a decrease in x will lead to increase in y. That is, x and y are in the opposite direction. Then we say correlation is negative. We also talk about perfect positive and perfect negative. Whenever the correlation is exactly equal to 1, then we say correlation is perfect. Plus 1 perfect positive, minus 1 perfect negative. So correlation is, the coefficient of correlation always takes a value between minus 1 and plus 1. If it is exactly equal to minus 1, then it is perfect negative. Exactly equal to plus 1, perfect positive. If it is equal to 0, it is zero correlation or no correlation. If it is greater than 0, positive correlation, less than 0, negative correlation. Now the question is how to measure this correlation between the variables. There are three measures of correlation available. First one is scatter plot, then we have Carl-Pearson's method, and then we have Spearman's rank method. In the scatter plot, we just plot the given values of x and y in the xy plane, and we see whether any sort of linear relationship exists. So take suitable scale for plot x values on the x-axis, y on the y-axis, mark the pair of observation and see whether you could observe any straight line, or imagine a straight line such that the points are closer to those. In that case, we can say correlation exists. So scatter plot is the graphical way. It just tells us what is the type of correlation, whether it is positive, negative, perfect positive or perfect negative, but the exact amount is not given by the scatter plot. So that is the major drawback of the scatter plot. To overcome this, we use Carl-Pearson correlation. Carl-Pearson correlation is also called as product moment correlation. So if you remember, moments mu1, mu2, mu3, mu4, moments denoted by sigma x minus x bar divided by n to the power of rth moment. So we'll be using these moments. The first moment is this raw moment is mean. Then we have the moment sigma x square or sigma x minus x bar whole square, which is variance. So the simple meaning of moment is mean and variance. So we'll be using the concept of mean and variance to obtain the coefficient of correlation. Hence this method is also called as product moment correlation. It uses the given values of x and y. Mean is based on the all values of x. Variance is also based on the given values of x. Whereas in case of Spearman rank correlation, we will be not using the given values of x and y, but will be using the ranks allotted to x and y. That's why it is called as rank correlation. So whenever you have some qualitative data, you have some grades, that is non-numerical data, you can apply Spearman's rank correlation by assigning the ranks in the order. So Carl-Pearson uses x and y in all those cases of data, numerical data, where you have x and y values recorded. If you want to obtain the amount of linear relationship between x and y, you could apply coefficient of Carl-Pearson's skewness correlation. Similarly, so let us discuss the scatter plot in detail. So you have x and y values given. Take x and y values, plot them, and you will observe some sort of graph here. So there are 6 categories of plots you can observe here. So in the first case, when you take x and y here, and you will plot the pairs of observations, you will observe that your x and y are somewhat like this. Imagine a straight line. This is the straight line. Straight line is such that it is close to most or all of the points. So in this case, that is, if you observe a straight line from the origin to the infinity comma infinity, or you can say that the line is making acute angle with the x-axis, in that case we say correlation is positive. The one of the special case of positive correlation is all the points are exactly lying on the straight line. You get a perfect straight line, then you can say that r is equal to +1, perfect positive correlation. Now similarly, if you have points scattered throughout the xy plane, you cannot imagine a straight line here such that it is close to most of the points. In that case, you can say that r is equal to 0. No relationship exists. No relation of any sort here. Neither linear nor quadratic or logarithmic and so on. Similarly, in the next category, you could have x and y values, but you will observe that the straight line what you are imagining is like this. That is, it is making an obtuse angle with x-axis. in that case you can say that R is negative or the correlation is negative. A special case of negative correlation is that you will have all the points lying on the straight line which is making obtuse angle with the x-axis. So in that case you can say R is perfect and negative. So you could observe some other behavior, a pattern which is not linear, which is not in straight line, any curvilinear relationship or the relationship like this where your x values are in the j pattern or it is somewhat like this in the s pattern or any other curve. In that case also we say R is equal to 0, but x and y are related there. Here there is no relationship at all, but here we say x and y are non-linearly related. Non-linearly related in the sense they could be related in the function of higher degree other than 1, logarithmic relationship, exponential relationships, and so on. So we just say they are not linearly related, hence we say R is equal to 0. So the concept of correlation, it is always amount of linear relationship. Amount of linear relationship. So this is how we decide using the scatter plot. Plot the given pair of x and y values and observe what is the type of the graph and comment on the type of the correlation. So as I said, it doesn't give you the exact amount of relationship or the exact value of the correlation. That's why we use the next method, which is called as Carl-Pearson's method, or also called as product moment correlation. So here we use the term as coefficient of correlation. This is indicated by R or sometimes by RK, K for Carl-Pearson correlation, and the basic definition of Carl-Pearson correlation is ratio of covariance to the square root of the product of variances. So you have two variables here. Compute the variance for both the variables x and y, and we have what called as covariance. Covariance is defined as the mutual variance. What is the variance in y? What is the variance in x with respect to change in the other variable, and that is captured by the formula sigma xy by n minus sigma x by n into sigma y by n. So this is how the covariance is defined, and you know the definition of variance. Variance of x is sigma x square minus x bar whole square by n, and variance of y is sigma y square by n minus y bar square. So if you substitute these values here, you get R is equal to sigma xy by n minus sigma x by n sigma y by n divided by the square root of sigma can say x square by n minus x bar square into sigma y square by n minus y bar square. So if you do some little algebra here, the formula can be further simplified into a beautiful form, and hence you can say that R is equal to n sigma xy minus sigma x sigma y divided by n sigma x square minus sigma x whole square into n sigma y square minus sigma y whole square. So this formula is easier to memorize, as well as it avoids the calculations of mean as well as the variance. So if you have been given with the values of x and y, multiply them, obtain its total, obtain the total of x, total of y, square the value of x, obtain its total, square the value of y, obtain its total, just substitute those values here. That is your Carl-Pearson coefficient of correlation. So you have to memorize this formula, n into sigma xy minus sigma x sigma y divided by square root of n sigma x square minus sigma x whole square n sigma y square minus sigma y whole square. Should be careful here. This is total of x square. This is total of x the whole square. Total of y square minus total of y the whole square. This is Carl-Pearson correlation. Now this Carl-Pearson correlation has some properties, and the first and foremost, as I already said, is that it always lies between -1 and +1. It can't be less than -1, it can't be more than +1. And if the special cases are R equals 0, no correlation, R equals +1, perfect positive, R equals -1, perfect negative. So if your R is very much close to 0, say for example minus 0.32 plus 0.16 or 0.44, we say correlation to be low. If your R is close to plus 1 or minus 1, close to plus 1 or minus 1, say for example 0.89 plus 0.95 and so on, we say correlation to be high. So you could have negative high correlation, positive high correlation, negative low correlation, positive low correlation. So all based on the value, exact value of R. The second property is that it is independent of change of scale as well as change of origin. Independent of change of scale. So if you remember, while discussing mean, I talked about the change of scale as well as change of origin. Change of origin means that you are shifting the origin from the xy plane to some from origin 0, 0 to some plane A and A. For example, say you have some xy values here and this is with respect to the origin 0, 0. Instead of that, you will move your origin to A comma B. X is equal to A, Y is equal to B, and then you will observe that your correlation plane or xy plane is like this and the imaginary line is like this. So change in origin can be explained as defining the new values for the variables x and y. Say, let me take the given values as small x and small y. We define capital X as your small x minus a and capital Y as capital small y as capital Y minus b, where this a and b are said to be assumed mean of x and y. So you could pick any values, one of the values of x as a, any other value as of y as b. It could be the minimum or maximum or the middle value or the first value. The choice is yours. That is your AB. So pick that a, subtract a from each and every value of x, rewrite the value of x, subtract every value of y from b, and you can call that as capital Y, which is equal to this set of y minus b. Now you will get new values for your x and y. If you use this x and y to compute correlation, whatever the correlation you observe for the new variable x and y, that will be same as your old variable xy. So that's why we say correlation is independent of change of origin. The concept of change of scale comes when you, after subtracting, divide the variables by some other number c and d. So as per, you can take the class width, or you could take c as the gap between two successive values of x. Usually we take 5 or 10, or if in case of continuous frequency data, if we have class width, we'll take the class widths as c and d. So this is said to be change of scale. So even in this case, after subtracting and dividing whatever the value of x, y you get, we'll observe that the correlation is same, and hence correlation is said to be independent of change of scale as well as origin. Third property is that it is independent of unit of measurement. If you remember, coefficient of quartile deviation, coefficient of skewness, we call them as coefficient because they are not dependent on the unit of measurement like rupees or age, years, height, centimeters and so on. It is independent of unit of measurement of x and y. So if you have x in terms of rupees and y may be some other variable, say year and price of gold, then you can say that R is unitless. It is neither rupees, it is not year. R is just a coefficient, so it is not dependent on the unit of measurement, and hence you could easily compare the correlation between several variables. So these are the three important properties of Karl-Pearson's correlation. So this correlation gives you the amount of linear relationship, but it doesn't give you the exact relationship. Say for example, I said the linear relationship is of the form y is equal to a plus bx. If you observe that y is dependent on x, in the previous example where I said price of gold is your y because that is your dependent variable, and independent variable is years. Whatever the year you are considering, that becomes the independent variable. So in some cases your x could be the dependent variable, y could be independent variable. So for a given pair of bivariate data x and y, we could have the relationship as y is equal to a plus bx or x is equal to c plus dy. So this exact relationship is in the form of linear line is called as regression line or regression equation. So after computing the correlation, the next step is you have to compute the regression. So regression analysis talks about finding the actual relationship between x and y. When I say relationship, I mean only the linear relationship, actual linear relationship. Here we only stick to simple regression, simple linear regression, that is linear relationship between two variables x and y. The general form of the regression line, as I said, you have two variables here, x and y. So you will have x is equal to some alpha 1 plus beta 1 times of y. So we'll observe x is the dependent, y is the independent. Using the values of the observed values of x and y, we'll estimate these coefficients alpha and beta. So this is called as regression line of y, x on y. When I say x on y, x is on the left side, y is on the right side. Similarly, you could have y is equal to alpha 2 plus beta 2y. So this is called as regression line of y on x. Now to arrive at the regression equations, we should compute what called as regression coefficients. Coefficients similar to the coefficient of correlation. So as there are two equations, we will have two regression coefficients indicated by bxy as well as byx. So bxy is called as regression coefficient of x on y. Regression coefficient of x on y. So it is given by n. In simple terms, when you know the values of correlation as well as the standard deviation, you can define bxy as r into sigma x by sigma y. First term is x, second term is y here in the subscript. So we'll have x in the numerator, y in the denominator. Similarly, this will be r into sigma y by sigma x. Sigma y stands for standard deviation of y, sigma x is standard deviation of x. So if you know the information on r as well as the standard deviation, you could use this formula to compute your bxy. If you don't have information regarding the Pearson correlation, standard deviations and so on, then you could use the formula similar to your Pearson, n sigma xy minus sigma x sigma y divided by n sigma y square minus sigma y whole square. So there is a change in the denominator here. Numerator is similar to the formula of r, n sigma xy minus sigma x sigma y, when in this case the numerator is same, n sigma xy minus sigma x sigma y, but in the denominator you will have only the terms related to x. Again, it is also easy to remember. The second term here is y, so in the denominator you will have terms with respect to y. Here you have x, so you will have terms related to x. So when you have the raw data x and y or frequency data given, in that case you have to compute the total of xy, total of x, total of y, total of x square, total of y square in order to compute the regression coefficients. Now once you have the regression coefficients, now you have to start building your regression lines. So as I said, there are two regression lines. The regression line of x on y, if you are building it from the given raw data, the equation starts like this. As I said, x on y, your x will be on the left side, x is equal to, we are talking about regression line of x on y. For the line of x on y, we need the coefficient x on y, so bxy into the second variable y minus y bar plus x bar. So from the data you will compute these three. You can compute the mean of x, mean of y, regression coefficient of xy. These two are the variables here. So substitute the values here. Say for example, you might get 0.56 as bxy. Y is the variable, which is y itself. Y bar, we are observing the mean as say 56. We are observing the mean of x bar as 34. So you have x on the left hand side. Now simplify this expression. You will get x is equal to 0.56y. When you simplify these three coefficient numbers, you will get some numbers. So let me say it is some 36 over here. So you have x is equal to beta 1 y plus alpha 1 constant and this. I have to really understand the expression here, x is equal to alpha 1 plus beta 1 y. That is, whenever you are observing y as 0, that is there is no y at all, then what is the default value of x? That is alpha 1, the first value, observed value. Similarly, when you say that x changes from one particular value, or you can say that there is a unit increase in y, then what is the change in x? So if y goes from 5 to 6, so there is a unit change, then there will be an increase in the amount of beta 1. So beta 1 is the unit change in x for unit change in y. Alpha 1 is the value of x when y is equal to 0. So this is your regression line of x on y. So I will be given with x and y. First step is compute the regression coefficients, compute the means x bar and y bar, substitute the values of the coefficients as well as the means, simplify the equation, that will fetch you the regression equation. A regression equation of x on y is used when you are in a position of estimating the values of x for a given values of y. Some y values are known, new y values are known, or the missing y values are known, for which you have to estimate the values of x. In that case, you could use the regression equation of x on y. So for a given y, what is the value of x? In that case, we will be using the regression line of x on y. The next equation is regression equation of y on x. When I say y on x, you will write y here, then you will have byx, y on the left hand side, first term is y. Regression equation of y on x, coefficient of y on x, regression coefficient of y on x, with the terms with x minus x bar plus y bar. So compute x bar, y bar, byx from the data, substitute them, simplify, the equation just reduces to y is equal to some constant plus some constant into beta 2. Again, beta 2 is the change in y for a unit change in x. If there is no x at all, if the value of x is 0, then the default value of y will be alpha 2. So this is about regression coefficients as well as regression lines. So in the correlation analysis, we try to evaluate or investigate whether there is any presence of linear relationship between x and y. If at all we are satisfied that there exists some relationship between x and y, linear relationship between x and y, then we go ahead and try to obtain the exact linear relationship between x and y using the regression analysis. Coming to the properties here, there are some important properties. As I said, these are the regression lines, straight lines. Therefore, a given bivariate data, they will always intersect. So if you look into the scatter plot, so this is the plot of your given bivariate data x and y. So now you will have two lines, regression equation of x on y, regression equation of y on x. Straight lines, two straight lines, obviously they will meet at a point, and the point of intersection here is x bar and y bar. Both the regression line pass through the mean of x as well as mean of y. If you observe that the lines are closer to each other, in that case you can say r is high. In the second case, if you observe that lines are not that close, they are far away from each other, or the angle between them is close to 90 degree, in that case you can say r is low. A special case is when r is equal to 0, you will observe that these are the points, the regression lines are perpendicular to each other. So the angle between them will be exactly 90 degree. So closer the regression lines, that is smaller the angle between the regression lines, r is high. Larger the angle between the regression lines, r is low. If the angle is exactly 90 degree, then it is an indication that r is exactly 0. So these are the properties of regression lines. They pass through x bar comma y bar. They have a single point of intersection which is x bar comma y bar, and they indicate whether r is high, low or 0. Similar to the properties of this, the properties of regression coefficients are also important here. One special property is that when you multiply bxy and byx and take the square root, that will give you the value of r. And all these three coefficients will share the same sign. You cannot have different signs for this, the numerical sign here, plus or minus. So if you observe that r is negative for a bivariate data, its bxy and byx both will be negative. If bxy and byx both are positive, then r will be positive. So if you know these two values, you can obtain r as this, but both the negative sign converts to positive when you multiply, hence you have to put the sign manually. Using this relation, what is the property? R has the same sign as that of bxy and byx. So if you are observing bxy as minus 0.5 and byx as minus 0.9, then your correlation value will be root of minus 0.5 into minus 0.9, which becomes plus 0.45, square root of 0.45. Take the square root of 45. You have to attach the minus sign because these two are taking negative sign. R will take negative sign. So no need to worry about the plus sign. If both are plus, automatically the formula gives you the plus sign there. So this is one of the important property of regression coefficient. So if you remember the concept of geometric mean between two numbers a and b is defined as square root of the product of those two numbers. Now similarly, we have square root of the product of bxy and byx. Hence you can say that R is the geometric mean of bxy and byx. R is the geometric mean of the regression coefficients. This is first property. And they share the same sign. The second property is that if you are observing any one of the regression coefficient as a value greater than 1, the other must be always less than 1. That is, you cannot have a situation where both are greater than 1. You cannot have a situation where both are greater than 1. You cannot have this case. Pick any bivariate data, this is not at all happening. Whereas the other thing can happen. If one is less than 1 and the other is also less than 1, that can happen. Or one is less than 1, the other is greater than 1, that can also happen. But never ever both the regression coefficients will take a value greater than 1, because we know the property of R. R lies between minus 1 and plus 1. If both these values are greater than 1, the product of these two will also be greater than 1, and square root of the number greater than 1 is also greater than 1, but the square root of the product is R, and R cannot be greater than 1, which implies that your bxy and byx never be greater than 1 together. But, or you can say if one is greater than 1, the other one must be less than 1. So this is how you could check your calculations. After computing your bxy, byx, you should observe that the signs are same. If both should be less than 1, agreeable. If both are greater than 1, then definitely you have made some computational mistakes. So this is about your correlation analysis as well as regression analysis. So I have shared the file with the next practical problems on correlation as well as regression 1. I'll show the calculation for one problem. Please do the other problems.